So dear student, continuing the chapter number 2, the third part, and in this third part, we will discuss a very important terminology which is called ROC and AUC. So what is ROC? ROC stands for Receiver Operating Characteristics. In some terminology, like in digital signal processing and other electronics, ROC is also called region of convergence. But here in machine learning, we refer it as receiver operating characteristics, and AUC is like area under the curve, right? So and basically when we do ROC minus AUC, basically this is the performance measurement for classification problem at various threshold settings. So whereas accuracy is the ratio of number of corrected prediction to total number of prediction. So this is the basic things which about the ROC and AUC. But to know about the ROC is basically it's the probability curve. So whenever you hear about ROC, so the word probability should come in you, and it is from 0 to 1. While AUC, area under the curve, which is to represent the degree or the measure of separatability, sometimes it separates the two values, here in the graph you can see it separates, like the diagonal graph you can see here, and it's a separation between the upper and the lower. So the upper one is called the curve, which you can see with the cutoff value it is written. So that is basically that is called ROC curve, or we call it as a receiver operating characteristics. So basically, this one AUC, it tells much the model is capable of distinguishing between classes. For example, if you see higher the AUC, better the model is at predicting 0 class as 0 and 1 class at 1, right? So this is basically the normal definitions and the aura of ROC and EUC, and it is being calculated by the confusion matrix again. So confusion matrix is the father of machine learning, validation and accuracy, precision, and all these things. So basically, on the x-axis we put false positive rate from 0 to 100, and on the y-axis we put true positive rate, right? Which is called sensitivity. And on the y-axis and the x-axis we put false positive rate, which is called 1 minus specificity. So and here there is some point you can also see cutoff for the high performance model. Some points are we call it cutoff, and some points which is on the line of AUC we call no discrimination AUC at the 0.5. So moving to the next slide, there is a questions whether the cat is obese or is not obese, and we will see with respect to ROC and AUC. So as I told you, ROC is with the probability. So the probability is from 0 to 1, and there is no mid probability like 0.5, so which is more with the AUC. So when we are doing the logistic regression, the y-axis is converted to the probability, and that is the cat is obese, right? So the blue one is mean cat is obese, and the 0 is not obese. So if someone told us that they have a heavy cat that weighs this much, right? So in this case, what is the what is the output here? And the curve would tell us that there is a high probability that the cat is obese. So here you can see the cat is obese, okay? And then the curve would tell us that there is a low probability that the cat is an obese, right here. So if there is with the lower curve, right, so it means it is a it's not an obese, right? And there's low probability, okay, while here is a high probability, so it's matching with the 1. So with the 1 it's it's an obese, and the point if it's near to the 0, so it's not obese. So it's very obvious in that case. So the logistic regression tells us the probability that a cat is obese based on its weight. So one way to classify cat is to set a threshold value. Like for example, if we say 0.5. So if let's suppose we say if the value is more than 0.5, it is an obese, and less than 0.5 is not an obese, right? So this is also one of the function we can say, and in AI also This is very important function and can be used in like fuzzy logic. This function can also be used when we specify whether it's greater than 0 or less than 0. And we classify all cats with the probability of being case obese, like greater than 0.5. And here we classify all cats with the probability of being obese less than or equal to 0.5, not obese. So here in this one, what do you think? Is it obese or not obese? So it's definitely obese because it's more than 0.5. Okay. Here are the weights of the 4 cats. Okay, that we will say know whether they are obese or not, right? So in this one, and here are the weights of the 4 new cats that were known as an obese, right? So here this is definitely obese because more than 0.5, 0.5, 0.5, more than 0.5, right? One predict obese but not in the obese, right? Okay. uh yeah, 3 predictor obese are obese. Okay, so here one is misclassified here. Okay, and 3 are is correctly classified. And here you can see and this was these red were not obese. Okay, and that's correctly classified, not obese, and this is not obese. And another one, like the blue were, one of the blue is obese, but it is classified as like not obese, so it means there is a one error. So on both sides, there is an error. So what will happen when we will use a different threshold for deciding if the sample is obese or no? So in that case, let's see, for example, if like 4 are saying obese and 2 are not obese. So in that case, what is the probability? So here we improve the margin. Okay, so in this one we like 0.9. So we change the function here. So we will determine which threshold is the best for it, right? So see, we will see that which threshold is best for it, and accordingly we will decide. So if you made one confusion matrix for each threshold, it will result a large number of confusion matrix. To summarize all of the information, there is a new concept which is called there is a concept which we already discussed, ROC, which is receiver operating characteristics graph. So so what is ROC here, and you can see in ROC this graph is very interesting and it will give you a lot of information. And there is some area is being made, and which we call AUC, area under the curve, right? So there is a curve is being made, and the area under the curve is called like AUC basically. So just to just to give you more information about that one. So in this case, there are some values like true positive rate, which is on y-axis, tells you what is the portion of a B samples were correctly classified, and false positive rate, which is called 1 minus specificity, which is the false positive divided by the false positive plus true negative. So the x-axis show the false positive rate, which is the same as 1 minus specificity, and on the y-axis we have the uh, like uh, sensitivity, which is the true positive rate. So this green diagonal show where the true positive is equal to false positive. So this these diagonal lines tells that where is the differentiation or demarcation. Based on how many false positive I'm willing to accept, the optimal threshold value is either this or this one, right? So there are like two values you can see here. This is so you need to, like for example, in optimization subject, we also see that some values are optimal, and we need to see the optimal threshold value. So we need to see that which one we're gonna accept as optimal. Sometimes we have one optimal value and sometimes we have two optimal values, right? So the ROC graph summarizes all of the confusion matrix that each threshold produces, and then we are having AUC. So AUC is like very interesting, and it gives you the area, all the area you have it, right? So here there is no you're out of the points and you come to the area. So area covers a lot of space over here, and for the same concept. So AUC will allow to compare one ROC curve to another ROC curve, right? So by this way, you can compare one full curve with another full curve, or area with an area. So the AUC for the red ROC curve is greater than the AUC for the blue ROC. So we have two AUC. One is for the red one, so red one is upper one, and one is for the blue one, which is the lower one. So the blue one and the red one, the blue one is the shorter one, and the red one is bigger one. So like it covers one. The red one is covering the blue one. So suggests that the red curve is more better. It's like a more comprehensive, you can say. So although ROC graphs are drawn using the true positive rates and false positive rate, as we already know, sensitivity and 1 minus specificity, to summarize the confusion matrix, there are other matrices that attempts to do the same thing. Like for example, people often replace the false positive with the precision. So precision is equal to true positive divided by true positive plus false positive. And this portion of positive results that were correctly classified over here. So precision is also very interesting, and it also can be extracted and derived from the confusion matrix, and it's like dealing with the probability of the obesity. The proportion of the positive results that were correctly classified, and there were a lot of samples that were not obese relative to the number of obese samples, then precision might be more useful than the false positive rate. And here you can see here. This is because precision does not include the number of true negatives in the calculation and is not affected by the imbalance. If there's an imbalance, so it doesn't affect because there is no true negatives here. And this is the end of the chapter number 2. See you in the chapter number 3 for the machine learning.